Hello everyone, welcome to another video lecture on the chapter Solutions. In this video, we shall continue with our discussion on the colligative properties of solutions. Now in the previous lecture, we had discussed two important colligative properties, that is, the relative lowering of vapor pressure and the elevation of boiling point. Now in this video we will be discussing about the depression of freezing point and the osmotic pressure of solutions. Now let us talk about the depression of freezing point. Now when a non-volatile solute is added to a pure solvent, the vapor pressure of the resulting solution decreases with respect to that of the pure solvent. Now when we talk about freezing point is that temperature at which the vapor pressure of the substance in its liquid phase is equal to the vapor pressure in the solid phase. Or in other words, a solution will freeze when its vapor pressure equals the vapor pressure of the pure solid solvent.
Now the depression of freezing point is given by delta Tf, and delta Tf is equal to the difference of the freezing point of the pure solvent and the freezing point of the solution. So here delta Tf naught is the freezing point of the solvent and Tf is the freezing point of the solution, and delta Tf is the depression of freezing point. Now this delta Tf for dilute solutions, it is found to be proportional to the molality of the solute in the solution. So we can write this relation for delta Tf as delta Tf is equal to Kf into m. Now Kf is the constant of proportionality, which is also called as the molar depression constant, and it is also called as the cryoscopic constant. Now we already know that for molality of a solution is the number of moles of the solute per kg of the solvent. Now number of moles, as we know, is given by the mass of the solute divided by molar mass of the solute. So when you talk about molality, it can be written like this. So it will be weight of the solute divided by molar mass of the solute, which is divided by the weight of the solvent in kgs. And if we want to convert this into grams, we have to divide it by 1000. So this is the relation for molality of a solution. Now if we substitute this into the relation for depression of freezing point, we can get this relation. So delta Tf is equal to Kf into the weight or mass of the solute, that is the non-volatile solute, into 1000 divided by the molar mass of the solute into the weight or the mass of the solvent. Now knowing the freezing point of the solvent and the freezing point of the resulting solution, it is possible therefore to calculate the molecular mass or molar mass of the non-volatile solute in the solution.
Now let us discuss another important colligative property of solutions, and that is the osmotic pressure of solutions. Now in order to understand osmotic pressure, we need to first understand the phenomenon of osmosis. Now when a solution is separated from its solvent by a semi-permeable membrane, there is a spontaneous flow of the solvent molecules from the solvent compartment to the solution compartment. The phenomenon is called osmosis. Here, the movement of the solvent is only in one direction, that is from the solvent to the solution, or in other words, from a region of low concentration to a region of high concentration. Now, when we talk about this semi-permeable membrane, the semi-permeable membrane is one which only the solvent molecules can pass through, but not the solute molecules. Cellophane, parchment paper, or the wall of a living cell can act as a semi-permeable membrane. Now, when we talk about osmotic pressure, we have seen that in this case there is a net flow of the solvent molecules through the semi-permeable membrane to the solution compartment. The flow of the solvent molecules into the solution through the semi-permeable membrane can be stopped by applying pressure on the solution site. Thus, the osmotic pressure of a solution is defined as the excess pressure that must be applied to the solution to prevent osmosis, or in other words, to stop the passage of the solvent molecules into the solution through the semi-permeable membrane. Now, it should be noted that if a pressure higher than the osmotic pressure is applied to the solution, the solvent will flow out of the solution into the pure solvent through the semi-permeable membrane, and this process is called reverse osmosis. An important application of reverse osmosis is the desalination of seawater, that is, the removal of salts from seawater. By applying pressure greater than the osmotic pressure, pure water can be made to flow through the semi-permeable membrane, and this water can be used for drinking purposes. The osmotic pressure of a solution is found to be directly proportional to the molar concentration of the solution and its temperature. Now, mathematically, we can write this as pi is proportional to C and pi is proportional to T. Now, in this case, we need to remember that pi is the osmotic pressure, C is called the molar concentration of the solution, and T is the temperature in Kelvin. Now we can rewrite this relation as pi is proportional to C into T, and we can further write this as pi is equal to C into R into T. Now here R is known as the solution constant, and its value is found to be the same as that of the gas constant. Now we need to also remember that the molar concentration C is equal to the number of moles per volume or per liter of the solution. And here N denotes the number of moles of the solute, and V is the volume of the solution in liters. Now if we substitute this into the relation for osmotic pressure, we get pi is equal to N by V into R into T. We can rewrite this relation as pi into V is equal to nRT. This relation is also known as Van Hoff equation for dilute solutions. Now, number of moles of the solute is given by mass of the solute divided by molar mass of the solute. Now, by substituting this value into the relation for osmotic pressure, we get pi into V is equal to mB by capital MB into R into T. Thus, measuring the osmotic pressure pi of a solution containing m grams of the solute in V liters of the solution at a temperature T, the molecular mass of the solute can be calculated using this equation. The value of R is taken as 0.0821 liters atmospheres per mole, and here pi is expressed in atmospheres and T is expressed in degree Kelvin. This method for determination of molecular masses is used for the determination of masses of proteins, polymers, and other macromolecules.